This presentation is on single base pair insertion or deletion in the context of prompt 4-1A. In this problem, we are given both the normal and mutant protein strands and want to investigate what type of mutation has taken place in between them, as well as the specific codons that are present in each strand. The normal strand starts with the start codon methionine and then reads tryptophan, phenylalanine, threonine, lysine, glycine, and continues on. The mutant protein starts in the same fashion with methionine and tryptophan, but then experiences a frame shift mutation as a result of either a single base pair insertion or deletion that then codes for isoleucine and histidine before being truncated by a currently unspecified stop codon. Our first step in solving this problem is figuring out whether a base pair insertion or deletion has taken place. Using the codon table, we can find some of the base pairs present in both the normal and mutant strands. Since some amino acids can be coded for by several different codons, some of the base pairs remain unknown, but the possible pairs are included below their respective blank. I then went ahead and color-coded the base pairs that follow this point of disruption to help visualize the frame shift that is taking place. Since the third amino acid in the mutant strand is isoleucine, we know that the third codon of the mutant strand must start with an A. From this information, we can see that an insertion of a single A base pair is taking place and is frame shifting the rest of the bases to the right. Now that we know where and how our frame shift mutation is taking place and have identified a majority of the base pairs in each strand, we can start to fill in the blanks for what we don't know by comparing the known pairs in both the normal and mutant strands. Using the fact that all of the base pairs in the normal strand are after the A insertion are shifted one space to the right, it doesn't take long to find what base pairs are missing. It's also important to note that the final codon of the mutant protein strand is a stop codon, so that we know it starts with a U. After taking into account the insertion of the A base pair and resulting frame shift, all of the unknown base pairs can be filled in with 100% certainty. That is except for the last base pair in the normal strand codon that codes for glycine. This base could be a U, C, A, or G. Since this codon is left off in the resulting truncated mutant protein, it is impossible to know its identity with 100% certainty given the information in the problem. We now know that the normal strand reads AUG-UGG-UUC-ACU-AAA-GG, and then either a U, C, A, or G, and that the mutant strand reads AUG-UGG-AUU-CAC-UAA.